Structure activity relationship of nalidixic acid. Nalidixic acid is a synthetic antibiotic that belongs to the class of quinolones. The structure activity relationship of nalidixic acid is based on its chemical structure, which consists of a 1,8 naphthyridine core with a carboxylic acid group and a nitrogen atom at positions 3 and 1 respectively. Structure activity relationship of chloroquine. Molecular formula C18H26N3Cl. Chloro at the 8th position increased activity, while alkylation at C3 and C8 diminished activity. The replacement of one of its N-ethyl group with hydroxyethyl produced hydroxychloroquine, a compound with reduced toxicity. Addition of CH3 group at position 2 will reduce the activity as in sandoquine. Addition of CH3 group at position 8 will reduce the activity or totally lose the activity. The presence of diethyl diaminopentane as a side chain its optimum for activity as in chloroquine. The OH group addition in the side chain at ethyl group, the hydroxychloroquine, which is less toxic and produce the high blood levels but slightly lowers the activity. Any substitution at position 1, 2, 5, 6 will lead to reduce the physiological activity. Aromatic ring. The 1,8 naphthyridine ring system in nalidixic acid is responsible for its antibacterial activity. The presence of two nitrogen atoms at positions 1 and 3 of the ring is essential for its activity. Carboxylic acid group. The carboxylic group at position 1 of nalidixic acid is important for its antibacterial activity, as it helps to form hydrogen bonds with the bacterial DNA. Substituents at position 7. The presence of a substituted at position 7 of nalidixic acid is important for its activity. Substituents such as a fluorine atom, chlorine atom, or a methyl group increase the potency of the drug by enhancing its binding to the bacterial DNA. Stereochemistry. The stereochemistry of nalidixic acid is important for its activity. The S enantiomer is more active than the R enantiomer. Linker group. The linker group between naphthyridine ring and the carboxylic acid group is important for the activity of nalidixic acid. Modification of this group can affect the potency of the drug. Parallelly, the SAR of nalidixic acid suggests that the presence of a 1,8 naphthyridine ring system with two nitrogen atoms, a carboxylic acid group at position 1 and a substituent at position 7 are essential for its antibacterial activity. Structure activity relationship of aminosalicylic acid. Molecular formula C7H7NO3. It is a synthetic second line agent used in case of resistance pre-treatment and hindrance to first line therapy used in treatment of tuberculosis. It is used in the treatment combination with streptomycin and NH, and in a long-term treatment causes toxic effects and shown allergic reactions. For maximum activity, COOH and NH2 group should be at para position to each other. OH group may be at ortho or meta position but maximum activity at ortho. NH2 group, if replaced with chlorine or alkyl, activity is reduced. COOH, if converted to amide or ester, compound become less active. Structure activity relationship of sulfonamides. Sulfonamides are antibacterial compound containing sulfonamides group. These are synthetic chemotherapeutic agents. These were the first of antibacterial drugs to be used successfully for the treatment of bacterial infections in human. These are active against certain gram-positive and gram-negative organisms. These are mainly bacteriostatic in action and are used in the treatment of many diseases like blood poisoning, scarlet fever, sinus infections, urinary tract infections. The physiological activity of the sulfonylamide due to the sulfonyl radical in the molecule. The removal of the amino group from position 4 to some other position of the aromatic ring results into the complete loss of physiological activity. The presence of para-amino group is important for its antibacterial activity, and if this group is substituted, it should be done only by such radicals or groups which can be converted to free amino group in the body. The introduction of additional substituents into the aromatic ring reduce physiological activity. The substitution of the hydrogen of the SO2NH2 group with a heterocyclic aromatic nuclei gives highly potent compounds. When various radicals are introduced into the sulfonamide group, the physiological activity can either increase or diminished depending on the nature of the substituted radical. The presence of methoxy group in a mole is important for prolonged action of the drug. The methoxy group ensures the higher binding of the sulfonylamide with plasma proteins, which helps in prolonged action of the drug. The substitution of the NH2 group have also produced many potent compounds.